So I think we can start. So in the last lecture we started discussing about importance sampling. So the idea today is to wrap up our discussion around importance sampling, right? And the overall idea is to complete which implies basically PF hat, which is the estimator, the importance sampling estimator. This is equal to 1 by n. Okay. So this is something we already discussed last time. We discussed one more fact, and that fact is that this estimator is an unbiased estimator. We saw that it is an unbiased estimator because if you take expectation of this P of f hat, you end up with P of f. So that's why we saw that it is an unbiased estimator, and we discussed that. But why did we start talking about importance sampling? Because Monte Carlo simulation was already there. So why did we talk about importance sampling? What was the?
We needed many samples in Monte Carlo.
Correct. Because the Monte Carlo sampling or simulation has a very slow convergence, which means the variance is more. And so we started talking about this importance sampling, right? Which means this HXX, which is known as the importance sampling density or importance sampling density, needs to be selected in such a way which will reduce the variance of the estimator, right? Otherwise there is no point. If it is increasing the variance, then we should use Monte Carlo only, right? So we should select HXX such that the variance of the estimator is minimized, right? We should select this HXX, the importance sampling density, in such a manner so that the variance of the estimator is minimized, variance of PF hat is minimized. Because remember, coefficient of variation is equal to sigma by mu, and that sigma is this standard deviation of this estimator. So reducing this sigma means reducing coefficient of variation. Reducing coefficient of variation means that you will converge now at less number of samples. That is the idea. Is that clear? So if that is clear, then can you tell me how should we estimate hxx or find out hxx in the ideal world? In the ideal world, what are we supposed to do to find out hxx? What should be my hxx in the ideal world? How can I find that out? Forget about, I am using the term ideal because that will become clear later, but you can ignore the term ideal for now and tell me, how do you think we should find out this hxx? Let me change the question. Suppose I have two hxx. Which one is better? How will you select it? Suppose I have hxx1 and hxx2. Which will have minimum variance. So then what is the ideal hxx? 0 if possible. If not possible, what? Hxx that minimizes the variance. So how will you find it out? You will solve an optimization problem which will minimize the variance of the estimator, and the hxx that minimizes the variance of the estimator is my ideal hxx, assuming convex function and all those things that I converges to something, right? All of you follow this one? That my hxx, if I have to find it out, I know that my objective is to minimize the variance, because minimizing variance means faster convergence. So my objective is to minimize hxx. If my objective is to minimize hxx, I should find out hxx by solving an optimization problem. Everyone follows this? So then, to find hxx, we solved the following optimization problem. To find hxx, we solved the following optimization problem. So can you tell me the optimization problem? I want to find out what? H. So h is my design variable. hxx, let's call it star. Among the different possible hxx, I am going to select one which should minimize the variance, right? Variance of the estimator. So variance of PF hat, variance of PF hat. What is PF hat in this case? 1 by n summation I equal to 1 to n, I am not writing that, multiplied by the indicator function xi multiplied by weight xi. This is the estimator, right? This is my PF hat, and I am looking at the variance of PF hat, and I am saying that the hxx that will minimize my PF hat should be my variance, right? Is that all, or do you think there should be something else? Do you think this is all that we need, and by solving this problem I can find out hxx, or are we missing something? From an optimization point of view, is this all, or are we missing something? What constraint? So you are saying that some constraint we are missing. So what is that constraint that we are missing, or what are the constraints that we are missing? hxx will not be constant, and it will not be, because we will solve a variational differences will take. So hxx is a function, and we will treat everything as a function. So that is taken care of. So it will be a variational calculus kind of thing. Okay. So yeah, what do you know about hxx? It's a function. Any function? It's a PDF. So that means it should satisfy the property of, what is the property of PDF it should satisfy?
Non-negative and
Non-negative, okay, and
integration
should be equal to 0. So then my constraint should be integration over hxx should give me 1. So this is subjected to integration of hxx dx is equal to 1, right? This is the obvious constraint that I have to handle. You follow that, right? Okay, so this is the problem statement, and if you can solve this problem, you are ready to find out hxx. Okay, in the ideal world. Okay, why ideal world will, yeah, go ahead.
Why can't hxx be directly a Dirac delta type of function because its variance will be the least possible?
Correct. hxx can be a Dirac delta function. Dirac delta is also a PDF, but your objective is not to minimize the variance of hxx. Your objective is to minimize the variance of the estimator. So what you are saying, that variance is 0, but of the PDF. Your objective is not to minimize the variance of the PDF. It's to, so you will want PF hat to should be a Dirac delta, right? Okay, so this is what we are trying to solve, right? Everyone follows? So this is what we are trying to solve. Let us look into this variance expression and let us see if we can simplify it and if we can work with some subset of that. So we will focus on this term, okay, and let's call it A, okay, or O. O means objective function, let's call it O. So O is equal to variance of that term, right? Remember what are xi? Xi are samples, any sample, or it has some property? IID. So what I want is the independent part. So if xi's are independent, is variance of this, the variance can go inside, there will be no covariance part, and 1 by n will become 1 by n square. So O is equal to 1 by n square summation variance of if xi wxi, right? Now I want to write variance in terms of expectation. What can I do? How is variance related to expectation? Expectation of x square minus expectation of x whole square. Let us do that. So expectation of, you said expectation of x square. So expectation with respect to hx, remember that. Variance also with respect to hx, I have not written that. Okay, x square, right? What is I square? I square is I, because I is an indicator function, 0 or 1. 0 square is 0, 1 square is 1. So I square is equal to I. I f of xi multiplied by w square. W is not an indicator function. W square of xi. This is just the first term. What is the second term? Expectation of the total quantity whole square. What is expectation of the total quantity? It's an unbiased estimator. Therefore, expectation of the estimator is equal to PF. So, and the square of that. So, it should be PF square. Everyone follows? In last lecture, we discussed that for an estimator to be unbiased, expectation of the estimator should be equal to the PF, the quantity you are trying to estimate, right? Now in this case, And we also showed that importance sampling is an unbiased estimator, which means expectation of the estimator will give me the total, the actual quantity. So that therefore expectation of the estimator which is sitting inside, if I include the n term, I mean whatever it is, right, then it will come out to be PF. So which means minus PF square. Okay, clear? Now remember there is a summation sitting outside. Okay, and it is summation of multiple such terms. Now each of the term is a variance. It is summation of multiple variance. What is the range in which variance varies? What is the lower bound of variance? 0. Variance cannot be negative. So if it is summation of non-negative quantities, can I not easily look into one quantity at a time in a generic sense and minimize that? That will minimize all the quantities, because xi I will take x and do that. So I will convert xi into x, take only the term inside the summation and minimize that, because minimizing that for a generic x means minimizing it for all xi, right? So that means I am only going to work with the term inside the summation. Everyone agrees with that strategy? The second strategy is that what am I trying to minimize or maximize? Minimize in this case the variance. But by minimizing variance, what are you trying to find out? What is my design variable or design function in this case? H. PF is not a function of H. So to include that term makes no sense. Whenever I will take derivative or whatever, that term will vanish. So that means I am only going to work with the first term and try to minimize that. So I will repeat. Variance is a non-negative quantity and we have summation of multiple variances. So that means, and all of those terms are similar in form, which means if I take one term, make x generic and minimize that, that is equivalent to minimizing the whole summation. And now looking at that term, there is a PF sitting there. PF is not a function of H. So that means that term can be dropped, which means I am only going to work with expectation with respect to Hx, indicated function of x, not xi, x multiplied by w square x, and I will try to minimize that. Okay. So this is the term we will work with. Let's call it A. Okay. So A is what we are working with. A is equal to expectation with respect to Hx, if, the indicator function, if x, because I want to make it generic, it should work for any x, multiplied by w square x. This is what I want to minimize now. Okay. This is equal to integration if x multiplied by w square x. W is equal to what? What is w? Fx by hx. So fx square by hx square. Fx square x divided by hx square x multiplied by hx. With respect to that, I am taking the expectation. Dx, right? Which is equal to integration if x fx square x divided by hx x dx. So this is my final objective function that I will like to minimize, which means this problem statement that you see in red will now be written in terms of this which you see in green, which means so now hx x star is equal to, you are looking to minimize x integration if x f x square x h x x dx. This is what you are now trying to minimize, subject to integration of h x x is equal to 1. H x x dx is equal to 1. Okay. What do you think I will do next? The obvious step in constraint optimization? Lagrangian. I will use the Lagrangian and convert the constraint optimization into an unconstrained optimization. So, using Lagrange's multiplier, what do I end up with? H x x star is equal to argmin h x x multiplied by this objective function. So, integration of the indicator function multiplied by w square, which is fx square by fx square by hx x dx plus lambda times, that is the constant, integration of hx x dx minus 1, because in Lagrange multiplier the right hand side should be 0. So, integration of h x x dx minus 1. Okay, any doubt? This is fine. In both the integrations, you note that the integration limit is minus infinite to plus infinite, which means the two integrations can be combined. So, this is, if I combine this, what will I get? I will get integration ifx fx square x divided by hxx plus lambda times hxx dx, okay, minus lambda, right? Okay. So, now again, previously I said that because expectation, it was summation of variance, I will only work with one variance, right? Integration is nothing but summation, which means I am only going to work with now the term inside the integration, and I will try to minimize that. Okay. And remember, this is variational calculus we are now looking at. So, I will take the variational derivative with respect to hx. Hx is a function, so I have to take a variational derivative with respect to that. Okay. So, this term, okay. Keep in mind I am going to work with this term. So, taking variational derivative, what will happen to the first term? I and fx are not function of hx, so they are like constant, so they will stay as it is, and then I have a 1 by hx which will become minus 1 by hx square. So, I will end up with minus I f x f square x x divided by h x x, right? and then that should be multiplied with the variation of the function delta h, so that I am not writing, but that should be multiplied by the variation of the function delta hx, which I am not writing because that will cancel out, plus the second term hx will become delta hx directly, so lambda, and then total into that delta hx term is there, is equal to 0, right? Okay, same rule, it's just that now the derivatives are with respect to function, so it's variational calculus, that's all. Otherwise nothing changes, and because it is variation, so instead of becoming 1 it becomes delta hx, and same thing, okay, because it's variation. So what is now hx equal to from here? So this term has to be equal to 0, this will be equal to 0. So what is hx then? Which implies minus I fx, f square I guess, fx square x divided by h x square x plus lambda equal to 0, which implies h x x is equal to what? Simple calculation, if square is equal to if. So I will not write if square, makes no sense. I will write if multiplied by fxx divided by square root of lambda, right? hxx is equal to ifx fxx divided by square root of lambda. So this is my optimal importance sampling density, but unfortunately it's a function of lambda, which I have not yet estimated. So I need to estimate lambda, and if I can estimate lambda, this would be my answer. Clear? What did I do? Just to recap very quickly, we started with this minimization problem. Then we said that okay, there is that variance I will expand, and then one term is not a function of hx. We just removed that. We also said that summation of positive quantities we can work with 1. So we took that, and then that gave us this problem statement. We used the Lagrangian to convert it into a single thing, and then we worked with only the term that is inside the integral. Okay, and yeah, and we could do that because the term inside the integral is positive, by the way, that's why. Okay, so we worked with that, and that's all. Then we took the variational derivative, equated to 0, and that gave me my hxx. So 3-4 simple steps, but my hxx turns out to be a function of lambda, the Lagrange's multiplier, which means I need to find out Lagrange's multiplier. How will I find it out? Iteratively Lagrange, that's too headache. I don't want that. Some easy way you say. I mean, when you can do it directly, why will you do iteration? And anyways, lambda most of the time you don't do iteration. You do iteration when it's a soft constant. Generally, you try to find out the exact lambda. So how will I find out lambda? What is hxx? PDF. So you will integrate that, and that should be equal to 1. That should allow me to find out lambda, right? So since hxx is a PDF, integration of hxx should be equal to 1, right? Which implies in 1 by root lambda, is it function of x? It should come outside. 1 by root lambda integration of ifx fxx dx is equal to 1, right? What is this integration equal to? This you should be able to tell. What is this integration? excluding 1 by root lambda equal to? And what is expectation of I? What is that? Think about it. PF, not even hat, because there is an integration. PF hat will be if I do it summation. Isn't that the Monte Carlo simulation formula? Integration of the indicator function with respect to the original PDF, which is fxx. Is that not the Monte Carlo formula? Right? That quantity is equal to PF. This quantity is equal to PF, which means what is root lambda equal to? What is root lambda equal to? PF. Root lambda times PF is equal to 1. Root lambda is equal to PF. And therefore my final hxx is equal to indicator function multiplied by fxx divided by P of f. So this is my optimal importance sampling density. You can go and substitute it. You will see that the variance will come out to be 0. That's the minimum possible. But this is the most useless thing that you will encounter, because your objective is to find out PF. And you are saying the expression is in terms of PF. You remember I was saying in the ideal world. So in the ideal world you will know PF. So you will find it and tell me that this is the optimal importance sampling density. But if you want to use importance sampling to find out PF, this is of zero use. Clear? So this is known as the optimal important sampling density. Optimal important sampling density. And the variance being equal to 0 means you draw one sample and that is your result. Because that sample is your PF. So obviously it is going to be your result. If you draw one sample, you get probability of failure is equal to 1. One failure point you get multiplied with PF, which is your weighting function. So you get your PF, but you will never know your PF. So this is you cannot never use. Clear? So now, if you cannot use this, we now know that we need a hxx that should minimize my variance, but we also know that we cannot go the mathematical route and minimize something to find out hxx. So now comes your common sense. How do you think we should find out hxx? Can you suggest something based on whatever we have done till now? But if that hat is initial samples, you will do initial MCS, right? Suppose you are trying to find rare event. Rare event means initial samples will give you PF hat to be equal to 0. So this will be important sampling density will be something infinite or something like that. And that will not be so straightforward. Also, sampling from this distribution itself is very challenging, isn't it? How will you sample from, even if I knew PF hat, how will you sample from it?
But we have to find out PF hat from fx.
Okay. So to find out PF hat, you are saying you will sample from fx. Initial samples will give PF hat equal to 0. So that means you cannot use it. Okay, that was one part of the answer. The other part of the answer is that even if you have your PF hat, sampling from this density is not so easy. You have to find even with that indicator function. I mean, that's what you will do, right? How will you sample from this? So we need a strategy that is easy, which is easy to sample from also. You should not come up with a density from which I cannot sample, and I need another method to sample from there. So the distribution you are sampling from should be a Gaussian or a uniform or something like that, or a mixture of Gaussian, something like that, right? So what any strategy you can think of? Are you aware of anything that we have covered in this course that talks about something regarding failure? Limit state function, but that's a function. I want point, right? Most probable point or design point. So you are aware of one such point at least, which is the most probable point or design point, where at the vicinity of which you are expected to get good number of failure points. Remember what I said last time. The reason MCS has a low convergence is because you do not get enough failure point. I said the thumb rule is that if you get 10 failure points, you stop here. Right? Now this most probable point or design point is a point around which I can expect more number of failures. Correct? So then the most obvious strategy in importance sampling is to have an importance sampling density which is a standard Gaussian. I mean, it will not be standard Gaussian actually, but which is a Gaussian with unit variance, let's say, centered at most probable point, which means U minus U MPP or Z minus Z star will be a standard Gaussian. Z will not be standard Gaussian because the mean is shifted. So you are shifting that such that the mean is Z star, the variance remains to be 1. That is expected to give you more failure point because you are near the limit state, right? Many of the points will be on the failure side of the things. So that's a good choice of importance sampling density.
But we don't know the actual point where it is actually.
No, you will solve so that means, so he is saying that you don't know the most probable point, right? So you will first solve a form.
Okay.
Find out the most probable point.
That will be approximated, but
That is always approximate.
the thing is that you have already mentioned, like when it is highly non-linear, then this will not work. Then in that kind of
Again, you are getting confused. I said that when it is highly non-linear, what will not work? The result will be wrong. PF will be wrong. The most probable point finding out is not wrong. It's still the nearest point on the limit state surface from the origin, right? The most probable point you are finding out is not wrong. Using that most probable point with first order Taylor series to find out reliability is wrong. And that is wrong because you are doing a first order approximation. Here you are not doing that. Clear?
If you take a point, any design point, but in that vicinity, how do we say that most of the failure points
Where does the design point lie?
are nearest from the
On the limit state function. Now assume a Gaussian around that, what will happen? At least 50%, if it is linear, at least 50% point are on the failure side. Is it not?
no,
Even if it is not Gaussian, many of the points will be on the
that will not be in the limit state.
huh?
That will not be in the limit state.
MPP is not on the limit state.
No, design point will be in the limit state, but if we approximate near to the
No, you are not approximating anything.
taking the Gaussian, then we are taking probable points.
Correct? No, you are not taking probable points. Again, you are confusing. What are the samples you are drawing? Are the samples supposed to lie on the limit state function? When I was talking about IF, was IF always giving you equal to 0? So you are not supposed to have points on the limit state function. Why are you supposed to have points on the limit state function? You are supposed to have points on the failure domain. And you are supposed to have points on the safe domain also, but you want failure points, right? That does not mean it will be on the limit state. It will not be on the limit state, to be more specific. Very few points, or maybe if you are very lucky, you will get 1 point on the limit state. Any question? Okay. Okay. So one option is that I will place an importance sampling density with the center at the most probable point, and it will have some variance. Let's say that variance is 1 for now. Okay, you can always argue why should it be 1, and that there are different importance sampling density that comes up with different ways of modeling this variance, but most of them do not change the center. Okay, so this means this cannot be used. That's all it means. Okay. So how will the algorithm look like with the form approximation that I was talking about? So algorithm. Input is fxx and n. Okay. Step 1, you will solve the form problem to find out x star or z star. Okay. So use form to find out x star slash z star. X star is the design point in the original physical space. Z star is the design point in the standard normal space. I mean, that's the only difference. Both are essentially the same points, but in different space. Okay. And now, once you have this, step 2 is your importance sampling density to formulate. So H, and this is, you set it to be equal to phi z minus z star. What does it mean? So I am having this importance sampling density in the standard normal space, and phi means standard Gaussian. Z minus z star is standard Gaussian, which means Z is Gaussian with mean Z star and variance 1. That's what it means. What is phi? Standard Gaussian. For standard Gaussian, what is the variance? Okay, no, not that's okay. That's okay. Maybe others also were not clear to it when I'm writing it. Okay, clear. So this basically means that this is equivalent to saying that Gaussian of Z with Z star comma I. I because multivariate. It's not one variable, right? This is equivalent to this only, nothing else. Clear? Any doubt on this? Once you have this, then I don't think I need to tell anything else. The main challenge in importance sampling is to decide what is the importance sampling density. Once you know this, then it's straightforward. You would sample, calculate the weights, calculate the indicator function, evaluate that, and do the summation and divide by n. So basically after this, step 3 is you will sample, let's say Zi, ith sample from this phi of Z minus Z star. Step 4 is you will calculate W of xi. So you will transform this Zi into xi and then do it. Calculate W of xi and indicator function of f xi, and then once repeat n times step 3 and 4, I mean steps we will repeat steps 3 and 4 only, not the other steps. 3 and 4, and then your PF hat is equal to 1 by n summation IF xi multiplied by W of xi. Okay. I shifted the notation from the subscript to superscript because in books sample number is generally written in the superscript, variable number is written in the subscript. So that is why I shifted it. Today the attendance is not taken, right? Taken? Okay. Okay. What is going on? Okay. So that's all. The main caveat here is that the idea of taking the mean as the most probable point is kind of clear. But suppose I have multiple failure points. Then what will you do? You will take mixture of Gaussian. One Gaussian at one Gaussian at other, and a weighted sum of that. So you can take mixture of Gaussian. But even then, the caveat is that you can ask that why I? Why not some sigma square I? You can take sigma square I. People have taken sigma square I. People have even set the variance to be equal to inverse of the Hessian, H inverse. because then the variance has information about the curvature. Because as he was saying, it. So think about it, right? Suppose this is my failure limit state, right? In that case, this is my failure point. This is the unit variance, let's say. A much better sampling strategy will be if my Gaussian is in this direction, right? It should not go in that tangential direction, specifically if the curvature is very high, because you know you are not going to get failure points there. So, right? Clearly this variance would have information from the Hessian. So that's why people take Hessian inverse as well. Okay. There are adaptive ways of doing it. So there are many ways of taking this variance. So there are new strategies that keeps on coming up, which talks about how to select the importance sampling density. The algorithm is very straightforward, but there is still scope for coming up with better ideas for finding out this importance sampling density. In the projects, one of the project I gave was REIN, R-E-I-N. So there what they do is that they train a neural network, a generative model, and that generative model acts as a importance sampling density. And then once with that the samples you are getting, now you weight it with this thing and continue. So REIN, that paper that I gave, one of the papers in the projects, was actually based on this idea. Okay. I don't know if someone has taken it or not, but I don't remember. But yeah. Okay. So this brings us to the conclusion of importance sampling. The main challenge in importance sampling is to find the importance sampling density. You will never find the optimal one, but the best importance sampling density, and it's generally based on intuition combined with maths and all those things. Okay. You can mix. You don't need to take all the points, because you will anyways weight that, so those samples. You will anyways have a weight that will account for the fact. You are not going to get all points. You need some failure points, right? Yeah, that's okay. You don't need all. Anyways, we are not drawing infinite samples, so you are not getting all samples, right? Importance sampling is saying that, okay, I will weight it, and that will give me. Okay. So yeah, so that brings me to the end of importance sampling. So
if the optimal, so how are we making sure that there are more number of failure points?
that's what we did.
So we reduce the variance.
We predict the variance, right? Now, if the variance is minimized, what does it mean? Why are you trying to maximize more number of failure points? Because that will reduce the variance. Your objective is to reduce the variance. Your objective is not to ensure more failure points, first of all. Because we cannot reduce the variance, we are saying, okay, let's have this observation and now used it. If optimal sampling density, importance sampling density I could use, I will always use that, right? Why will I do it? That is the mathematically optimal thing possible. Okay. Okay, so one thing I want to announce actually. So some of you at least in the homework submission has not submitted the code. Rather you have attached it as a screenshot or PDF kind of thing. Codes are to be submitted, we are going to run it and check it. So anyone who has not submitted the code, write to me and submit it by email. Okay. I know your case, but there are others also. Okay. The code is to be submitted so that you can run it. Ideally there should be a readme file also, which should tell that if there is something we need to do to run it. Okay. So yes, the results you are getting from code should be pasted and that should be discussed. That part is fine. But the code should always be provided as an attachment. Okay. And yeah, the 8 MB limit is the maximum limit that Moodle New is giving me. So I will see if I can do something.
So that was the problem that is why AD last time.
Yeah, I know.
PDF was not getting it.
Yeah, you told me that, right? Because of the Moodle New, right?
Moodle because of the AD.
Because Moodle New has the 8 MB limit.
So there is only we can only attach. We can attach only one file in the Moodle. So how are we supposed to submit?
No, zip you are supposed to upload it as a zip file. So a zip file that will have a readme file, your code and the PDF. So in that sense, and we will unzip it. So in that sense, okay. But I understand the Moodle new issue. So I'll figure out if I can do something. If not,
lot of compressors, then I finally submitted it.
I know. If I cannot do it ultimately, then I think one option is to go back to Moodle, which allows 20 MB. I mean, I do not understand why the new version will have less than the old version. I mean, it is beyond me. Maybe I'm missing some option. I'll go and check if I missed something in the Moodle new. Okay. Okay. Thank you.